Thanks very much. It's a pleasure to have a few minutes here to talk to you about work we've been doing, applying AI to forecasting the weather and looking toward forecasts on longer time scales, seasonal, and maybe even at some point climate type forecasts. So this is work that's been done in conjunction or connection with several people. Jonathan Venn, a former graduate student here at UW, really spark-plugged a lot of this work. Nathaniel Cresswell-Clay is another graduate student, and Rich Caruana is at Microsoft. So let's talk for a moment about forecasts. What kind of forecasts you're most used to hearing? It's almost certainly weather forecasts. And we see a little plot here that shows, see if I can get my cursor. There we go. So on the horizontal axis, we've got lead time for the forecast, starting with just the first 2 weeks and going out to really could go out to a whole year. And then we have a qualitative description of forecast skill, excellent to no skill. And what we see in this plot is three little curves here. One illustrates the way our daily weather forecasts lose skill as we go out forward from a day or two forecast to something like 14 days, where we have almost no skill left from what we know about the weather today. So we know the initial conditions when we try to predict the evolution of the weather. That gives us a lot of skill at the short term, and we have fairly good forecasts. Then as we move out to longer range forecasts, what happens in this case is we are actually trying to predict deviations from the average weather. We want to know stuff like, is it going to be a wet or a dry winter? Is it going to be a hot or a cold situation? In that case, we are using the fact that the atmosphere responds on a longer time scale to things like sea surface temperatures and vegetation conditions, soil moisture, and so on, and try to get some indication about whether it'll be a, well, this happens if I touch too quickly here. Anyway, we'll have to see how I can do with the cursor before I make a big mess. But anyway, the point is we have a lot less skill at seasonal and subseasonal forecasts. Oh, well, yeah, that won't work for the people online, but I'm so used to being online, I didn't even think about it. Let's see here. So what's going on? Ooh. This one. Yeah. All right. Well, welcome back to live presentations. This is much better. We'll stick with this. Okay, so anyway, the point is that we do not have very good skill at these longer time scales. In fact, in between, we have almost no skill on forecasts looking for deviations from the average weather over a period of, say, 2 to 6 weeks. So let's take a look at how deep learning might change our ability to address all three of these forecast challenges. Okay, so I want to go back to something that Jonathan Venn did actually as an expansion of an assignment that he did in an AI class here at UW, where he tried to predict the weather in the middle of the atmosphere on a short-term time scale. And what we have here are plots of something called the 500 hectopascal surface. 500 hectopascals is a measure of pressure. 1,000 hectopascals is our pressure down to the ground. This represents the pressure about halfway up through the mass of the atmosphere. And it's a topographic map, just like those of you who hike and look at topographic maps might have seen at some point. We've got labels here that are actually in tens of meters. So this red line is 5,460 meters above the ground. And there's a little ridge in this region, a little trough in this region. So what's going on here is we're trying to predict 500 hectopascal height using only previous 500 hectopascal height data from a data set that's available from the European Center for Medium Range Weather Forecasting. This is the initial condition. This is a verification 24 hours later. And if we look at what's happening here, this trough region off California is coming onshore and deepening as it gets onshore. Okay, if we now turn to some forecasts, we could take a look at the weather forecast that was made using the same set of governing equations that were used in the very first weather forecast back in the 1950s on the ENIAC computer. And what we see in this case is that the trough doesn't deepen, doesn't close off into a circular closed low like it should. And this is a known defect of the equation that was used for that early weather forecast. They were just trying to get started. It's the only equation that we have, however, that will tell us what the 500 hectopascal height should be like in the future, given only information about that same level, the 500 hectopascal height in the atmosphere. Of course, we can do better job forecasting the weather these days very easily, but we use different equations that have many more terms and functions. Okay, so what Jonathan did is he trained a deep learning weather prediction model based on this historical 500 hectopascal height data, and it got it right. It got the deepening of this trough more or less correct. It's certainly not perfect, but far better than the equivalent equation-based model. Okay, so I think this is an important result that's going to underlie a lot of what we're going to talk about going forward, is the machine learning beats the corresponding equation-based numerical weather prediction. We can do better these days. We can do better, of course, by using more complex numerical models. But if we want a sort of apples to apples comparison, the story is that we can do better with the deep learning model. Okay, so I want to review a couple of things about why we should be so interested in replacing what is, to some extent, a successful approach to numerical weather prediction with deep learning. And so the quick review, numerical weather prediction consists of two pieces of computer code. One is a dynamical core that covers equations for conservation of mass, energy, and momentum. It covers the behavior of large-scale air currents, large-scale waves. Its numerical approximation can be evaluated mathematically for all kinds of things like order of accuracy. But operational models include more stuff. This dynamical core is encrusted with parameterizations. And by that, I mean that in order to see clouds and precipitation in a global model, the global models parameterize the clouds. They parameterize what falls to the ground. They parameterize the influence of the Earth's surface. In fact, everything you see in this picture is parameterized. The influence of the flat terrain on the lowest parts of the atmosphere is parameterized. There's a small scale mountain that's parameterized. All this stuff is parameterized, and the parameterizations are evaluated empirically. So this is different than what we like to think about so often, that we're solving fundamental equations for everything in our weather forecast. A lot of this stuff is actually all validated empirically, which of course is where we are with deep learning as well. And deep learning would have some very important potential advantages because NWP is very, very compute intensive. It's difficult, therefore, to produce many likely simulations of future states, whereas deep learning weather prediction reduces the time required for each forecast by potentially several orders of magnitude, which allows for a large number of multiple forecasts from slightly different initial states to give us a better probability distribution for future atmospheric states, and could help us better estimate the chances of extreme events, for example. Plus, as we look further into the future and we start to talk about seasonal forecasting and the influence of things in the Earth's surface, we don't have any equations for that yet. Okay, and in fact, replacing NWP-style parameterizations with a holistic sort of machine learning approach could be very important for Earth system modeling, and seems to be pretty successful in our early attempts at this. Okay, so let me briefly describe our deep learning weather prediction strategy. I'm certainly not going to go into the whole model, but like numeric weather prediction, we are going to create forecasts by recursively stepping forward in time. And we're just going to use a few variables in our forecasts, very unlike current NWP models, and we're going to use coarse resolution to characterize the atmospheric state. And we're doing this because it's a starting point for deep learning weather prediction, but also very importantly, the space-time resolution required to get a good solution to differential equations that underlie a lot of NWP introduces more degrees of freedom that are necessary to characterize the most predictable atmospheric states. Okay, so deep learning weather prediction, I'll just throw a few slides up about the building blocks here. We're using a cube sphere grid, which may seem like a crude approximation, but it's actually now being used in NWP as well. So we have 6 faces of this cube. It's very convenient for the 3x3 convolutional neural network stencils that we're going to apply. This is just like the little animation that Armida showed of a 3x3 convolutional filter stencil. We can wrap it around the edges of our cube nicely using something called the UNet architecture for our overall structure of the deep learning network. We're going to train identical filters to use on all 4 equatorial faces. So that's these 4 here. Then we're going to train another set of filters that are going to be used everywhere on the 2 polar faces, and we'll flip the sense of rotation between those 2 sets of filters because that allows for the difference in the spin of the Earth and the North and South Pole. And this is sort of a physics-informed network design, which I think actually has turned out to work quite well. I'm going to show you some results from our simplest model first, which just has 4 prognostic variables. And these are variables on a single 2D shell. So something like surface pressure, this 500 hectopascal height that I mentioned earlier, 2-meter temperature, temperature into the ground, that would be, and temperature in an elevated layer, are our forecast variables. We also prescribed 3 fields: top of atmosphere incoming solar radiation, a land sea mass, and topographic height. And here's a picture of the cube sphere again. We're going to look at stuff from a 48 by 48 point discretization of each face of the sphere that gives us about a 200 by 200 quasi-uniform resolution over the globe. Okay, so we're going to, first of all, show you an insanely good result with this model about how stable it is if you just integrate it forward from a starting point in time, which will be July 4th, 2017. Okay, and then what we have plotted here are 2 maps of the weather. They show this 500 hectopascal heights once again in color contours in decameters, so 5,400 meters is this hard to see color that actually has a blue line on it too. And then the black lines are surface pressure. And it's not too exciting in the summer. The pressure field is flatter. We trained our model with a loss function that minimizes the mean squared error in those 4 prognostic fields every 6 hours over a single day. We don't look further ahead than a single day. Our time step is 12 hours. There are no physical constraints in this model. That's not to say our model can't benefit by putting some physical constraints in, but there are no physical constraints. We just train it from the data. Okay, so here is 195-day simulation. So we run out to January 15th now. And what's happened is we see blue up here because we're now in winter. It's colder in the North Pole. The heights are lower. I wanted to point out on the previous slide, but this one is good enough as well. What's plotted on the right is climatology. That is the average weather on January 15th over about a 40-year period. So it's a smooth field because the day-to-day variations have been smoothed out. Then what we have in these other 2 globes are, one of them is the actual verification for January 15th, and the other one is the model forecast that's been run out. And of course, there's no predictability 195 days. We do not expect these 2 globes to match each other. Notice I have question mark up here. There's more to come with question marks, but we don't expect perfect agreement at 195 days. What I want you to think about is I want you to think like a GAN, right? I want you to be the discriminator. So generative adversarial networks, right? Which one of these is the real face, which is the fake? Which was from the model, which is from the observations? Now you can see little squiggly jagged lines in the surface pressure field. That's because they're being sloppy in our linear interpolation between the cubosphere grid and the lat long mesh. Don't worry about that. The question is, which one of these do you think is the real case and which one is the fake face, right? So you're not meteorologists. It's not easy for you to answer this question. But what I'd like you to sort of notice is that there are low pressure centers in both of these, and there are ridges in both of these global maps. And it's not super obvious which one is the one that's been run out for 195 days with the machine learning model. But in fact, this is the simulation. This is the real weather. Again, we don't expect them to match perfect, but the point is that we run out 400 time steps or so in our model, just recursively stepping forward something that was optimized over a single day, and we're not going to climatology, which is something that's a huge problem that would often happen. We're not going to climatology. We've got a pretty good looking face, I'd argue here. Okay, so actually, depending on how good I am on controlling this thing, I was going to jump forward. This is the actual animation. I'm going to try to jump this forward. But we're starting in the summer again, back in July. Things are warmer again. Now, if I can avoid messing stuff up here, let me see if I can get there. Again, okay, good. Here we go. We're going to jump ourselves forward here. Oops, I think we're going to jump ourselves. Well, let's try again. It won't take that long if we're forced to run it. But I thought I could grab this thing. And of course, I don't actually even. Foreign computer. Well, we'll let it go for a while. When it gets to winter, maybe we'll stop. We're in November anyway. If I keep talking, we'll get to colder climate.
What does a bad model look like here? Does it totally go off the rails?
You mean if we train a model that's bad?
Well, you keep learning, just use the regular governing equations and let it go.
Oh, the governing equation. If we use the regular governing equations, we'll get. We can run that out for a year, fine. It's not going to be a perfect forecast, so these two will not match, but it will simulate realistic weather better than our model. So where this is not a state-of-the-art NWP, you know, that we use for your 4-day weather forecast. But we are, let's see, so we're getting into March. You can see we're actually starting to come out of the winter season. And if I could, yeah, I'm going to just skip ahead in a moment in the interest of time. If I can, definitely going to skip ahead. All right. So it comes back though to January to July type weather, just from that top of atmosphere forcing. It's smart enough to do all that, even though it was only trained to minimize the mean squared error over a single day. Okay. The other thing I'd like to point out is the way we've managed to. This model is smart enough to replace the kind of parameterizations that we have in atmospheric models that we run for real weather forecasts. We have parameterizations that deal with the effect of the lower boundary at the bottom of the atmosphere. We're going to talk about how the deep learning weather prediction model, a slightly better version now that has 7 prognostic variables, is able to figure out what's going on in the boundary layer in a way that just doesn't, it's just another astonishingly good result, I'd argue, that gives us faith we can push this approach much further forward. So we're using a better to much more sophisticated models. So what we are looking at is 2-meter temperature forecasts at 2 paired sites, the Amazon and the adjacent ocean, Australia and the adjacent ocean. And what we're interested in is a 2-day forecast. I'm just going to look at what the forecast looks like. Remember, we have only data every 6 hours from our coarse resolution deep learning weather prediction model. So these are piecewise linear curves for 2 days, connect data every 6 hours. The oceans are in blue. The land areas are green for the Amazon, red for Australia, and the dashed lines are the data, the solid lines of the deep learning weather prediction model. So we see over the oceans, as we expect, there's little temperature variation, and that's no big surprise. We're, of course, doing a good job forecasting this slowly varying quantity, and it has a land-sea mask. So we're not surprised about any of that, right? But what is surprising here, right? You should hopefully be all surprised about something if you've been out in the desert or in the jungle. And the story is that the model has figured out there's larger diurnal variations over Australia, about 10K, 10 Kelvin, whereas the diurnal variations are half that big over the Amazon. And remember, the set of filter coefficients we trained has no geospecific data, right? So there's no geospecific neural network weights in our training. We're using the same set of filters everywhere, all around those equatorial faces. But it probably understands from total column water vapor, the diurnal temperature range should be smaller over the Amazon. So it's really pretty amazing that it's managed to do this much with so little as inputs. Okay, so I kind of lost track of where I should be, but we're getting near the end here. So I'm going to just jump forward to thinking about how this kind of thing would be important once we want to move to deep learning Earth system models, because that's, as I mentioned earlier, where we start to connect up stuff that's forcing the atmosphere on longer time scales, seasonal or even multi-year time scales that we don't know how to put into the model using equations. So this is something called normalized differential vegetation index. And what happens is satellites sense infrared radiation coming back, well, in the near infrared, and then also the actual red visible light coming back. Look at the difference between the two, and they can figure out whether we have healthy or stressed vegetation. This data set goes back to the 80s. And if we look at the NDVI signal from the Great Plains drought, for example, we can see all this stressed vegetation. This is stuff we should be putting into our models that we can't really do right now. But the deep learning approach could be much better for that. Okay, and satellite remote sensing is, of course, the future. There's a whole lot of other variables that are being sensed these days. This one goes back a long ways, so we're happy to have it for training. But there's a lot of new variables that are being picked up by satellites over the last 10 years or so, and there'll be more and more going forward. This is the way we can do our modeling in the future. Okay, so I've talked a little bit about some of our successes. I just want to say one quick word to the larger AI community here. Let's think about a couple problems. Are these the same problem, cat or dog, or make a 4-day weather forecast, right? So, of course, what we did with our CNN, convolutional neural nets, is a sort of behind the curve way to do image processing. People use transformers and other things now, and attention is big. in AI for a lot of stuff, natural language processing. We try to, attention tells us in AI, we want to find the key features in our image. We want to know what we can ignore. We want to ignore a lot of stuff. That's really almost the heart of attention, is what you ignore, right? But maybe that's not what we want to do if we want a 4-day weather forecast, because small changes in the atmosphere can turn out to be important 4 days in the future. And so I just kind of throw that out as an example of collaboration between machine learning experts and atmospheric scientists would be helpful to move us forward here, instead of just trying to take something that the machine learning people have worked out and directly apply it. Okay, so conclusions. Deep learning weather prediction has the potential to revolutionize weather forecasting, echoing the impacts produced by the introduction of NWP in the 1950s. That revolution was based on two things: new computational capabilities in the form of the ENIAC and basic CPU-based computers. Now we have GPUs and a really different architecture, even in the hardware end of the world, that can make a difference. And of course, they had basic numerical analysis that got them somewhere in the 50s. We have much more sophisticated understanding of AI these days. Deep learning weather prediction can learn dynamics and physical parameterizations at the same time. This could be crucial for the Earth system modeling approach and longer-term forecasts at seasonal and subseasonal timescales. The speed of deep learning allows us to use much larger ensembles. Now, having a large ensemble is not in and of itself the whole story. It has to be a good representation and give you a good probabilistic description of what can happen. But it allows us, if we have a well-calibrated ensemble, to have a better idea of what's happening in the tails of the probability distribution and extreme events. These things can be stepped forward super fast. For example, a 320-member ensemble of 1 month forecast stepped forward with a 12-hour time step requires just 2 seconds on an NVIDIA V100 GPU. It takes a while to train this stuff, but the inference is very fast. And finally, deep learning weather prediction can be generalized or system modeling, and may be particularly appropriate at that time scale. Also could be used to generate end user products directly. Things like wind power forecasts could be generated from wind power data, for example. And finally, although I didn't really talk about this, it can provide an on-ramp to climate modeling with deep learning.